Uh, all right. Good afternoon, everybody, or good morning, good evening, whatever time it is where you are. So it is a pleasure to welcome our speaker today. It's Benjamin Steinberg from the City College of CUNY, and he's going to tell us something about contractibility of the orbit space of Brown's p-subgroup complex, and he'll explain a new proof. Ben, please.
Okay, so thank you. So yeah, so my goal is to give a new proof. There are several proofs of this. So how exciting a new proof is, depends on how much you value new proofs. What I think is different about this proof is it's a bit more explicit than the previous proofs. The previous proofs tended to either use induction or some fancy stuff. And this one's very concrete. So I think it's kind of, my hope is it's sort of the proof that will hope, if this was ever to be in a textbook, maybe it could be a textbook proof, but maybe not. We'll see. So I need to begin with some background in order to explain the problem. So at least for a change, I'm not talking about semigroups. So there will be no semigroups in this talk. So that's, I guess, good news probably for most people. But the groups will all be finite. So that's probably bad news. Okay, so if you have a poset P, for some reason on my screen, I don't see the whole screen, but okay, I guess you guys can see it. So if I have a poset P, then the order complex of P is the simplicial complex you get by just taking the poset P as your vertex set, and you choose the chains to be a simplices. So this is just a description as an abstract chain complex, as an abstract simplicial complex. If you actually wanted to build this geometrically, you would take a vector space with basis P. Pretend P is finite. I only care about finite posets in this one. And then you could just take as vertices the basis vectors, and then you can take the simplex that they span, their convex hull of any chain, and that will be your order complex. So just as a simple example, if your poset is 1, 2, 3 ordered by the less than or equal to relation, then this is the order complex. Every single subset of 1 to 3 is a chain. Chain just means totally ordered set. And so 1 is less than 2, so I have an edge from 1 to 2. 1 is less than 3, there's an edge from 1 to 3. 1, 2, 3 is a chain, so I get to fill this in. A more interesting example is take the power set of 1 through 4 and remove the empty set and the full set. So the proper non-empty subsets of 1 through 4 under containment. And the order complex is the barycentric subdivision of the boundary of the simplex with vertices 1, 2, 3, and 4. I just drew some of the cells, but for instance, the set 1, 2, that contains both 1 and 2, and it corresponds to the midpoint here of the edge 1 to 2. If you look at 1, 2, 4, it contains 1, it contains 1, 2. So these three guys are all here in a triangle. Similarly, you have this triangle, here with 1, 4, 4, and 1, 2, etc. So basically, the vertices, so the barycenter of the barycenter of the set of the standard cell tells you which subset it is. So if I take the standard triangle with 1, 2, 4, its barycenter corresponds to 1, 2, 4, the subset 1, 2, 4, and so forth. But I don't take the inside of this tetrahedron because I got rid of 1, 2, 3, 4, and I don't have the empty set here either. So this is a standard example of an order complex of a poset. One thing that's always true is that if you have a poset with a maximum element or a minimal element, then its order complex is contractible. I wrote the poset's contractible, but people who do poset topology, they kind of say that a poset has a property if its simplicial complex has the property. So why is that? If you have a minimum element, then it's a cone point of your poset. You can look at all the non-minimal elements, and you can connect, because P is smaller than everybody, any chain I have here, I can throw P on and get a chain, and that makes it a cone point. And so you can just contract this whole thing down to the cone point. And this construction is functorial with respect to order preserving maps. If you have a map between posets and it preserves order, then it will send chains to chains. And if you want to geometrically realize it, the corresponding linear map that sends the basis vectors P to the basis vectors of your other poset will be a simplicial map in the geometric sense. So But I'm not going to really care that much about realizing these things geometrically. I'm just going to work with abstract simplicial complexes. Now, if I have a poset with a group action, so a G poset is I have a group G, and it acts on the poset P by order preserving maps, then immediately, I'm not sure where that symbol came from. Sorry, there's a typo here. I don't know where that symbol came from, so ignore that. Ignore this symbol here. I don't know where it came from. Oh, that's better. What's that over here? So anyway, there's a weird typo here. I don't know where this came from, so ignore that. It just appeared there mysteriously. If you have a G poset, oh, it's mod G. I see what it is. It's just that I don't know. The line got moved. Something weird happened here. I'm sorry about that. So let me just clear that. I see what went wrong. That's supposed to be mod G, and I don't know what happened. I must have moved something. Something weird happened here. That's just in the wrong spot. It's supposed to be delta P mod G. I don't know what happened to my slide. Maybe when I turned it to a PDF, it messed up. That's supposed to be delta P mod G. That's just a typo. I don't know how that happened. Anyway, don't worry about that. So this is a delta set. It's not a simplicial complex. So what is a delta set? A delta set, if you've been forced to teach from Hatcher, you know what these are. These are basically like a simplicial complex. They're cell complexes built by gluing triangles. But what makes them different from a simplicial complex is that the intersection of two triangles doesn't have to be a triangle. And also you're allowed to, if you like, identify, I didn't do it in this example, but you could do something like a dunce cap, where all three edges of the triangle get identified to each other. So you're allowed to glue triangles, but it's less rigid than a simplicial complex. You can have things like a loop, that's okay. Multiple edges is okay. Or in this example here, what I'm doing is you can imagine, or what I'm trying to indicate is in this picture, where's the thing that lets me draw on it? I thought it's supposed to let me draw. Okay, see this edge and this edge are getting identified. This edge and this edge are getting identified to make this cone. But this edge is not the same as this edge. So that's why I have 2, 1, 2 edges. And then the green cell is the front of the cone and the pink cell is supposed to be the back of the cone. So in a delta complex, you have a little bit more flexibility. You can do stuff like that, which you're not allowed to do in a simplicial complex. In a simplicial complex, the triangle is determined by its vertices. But here I have 2 triangles with the exact same vertices. And the reason you get this when you factor out a simplicial complex by coming from a poset by the G action is basically because trying to stop this. I'm accidentally blocking my screen here, making it hard to read my screen. Okay, I don't know why that's there. So the problem is, imagine that you have some guy P which is less than G. So P which is less than Q. And imagine that P is also less than G times Q. But imagine that you cannot choose this G to be in the stabilizer of P. So then these 2 edges are not in the same orbit. There's no way the orbit of PQ and PGQ are different. And so I'll get multiple edges. And the same thing can happen with higher dimensional simplices. So you're no longer going to get that a simplex is determined by where its edges go. But still, you'll get something which is built out of gluing simplices. And that's the kind of example we're going to look at. And a standard source of G posets is what are called subgroup posets. If you have a class of subsets closed under conjugation, then, and you look at the induced order on these subgroups, then you're going to get a poset with a G action. Typically, these posets will be downward closed, these kinds of subgroup posets. So in this example, hold on, for some reason, it's not letting me exit this annotate. Okay. I don't know. Okay, let's see. I went too far. Okay, so here's one example, the Brown subgroup, p-subgroup complex. So I take a finite group G whose order is divisible by a prime P. I guess I forgot to say that P is a prime, but P, of course, is a prime, because what else would P be? And P should really divide, so this should be a power greater than 1, and M is going to be the part of the order of G which is not divisible by P. So I can write G, the order of G as a prime power times something relatively prime to that guy. And then SP of G is the poset of non-trivial P subgroups. Why do I want the non-trivial P subgroups? If I have the trivial subgroup, my poset will have a minimum. And if my poset has a minimum, it's automatically contractible. So it's not interesting. So Ken Brown, back in 1975, he introduced the poset of non-trivial p subgroups in connection with group cohomology and Euler characteristics. Actually, he even did this for infinite groups. He didn't care whether it was finite or not. And most of the interest in this has been for the finite case. And he proved something which is called the homological Silo theorem. What he proved is that the Euler characteristic of this poset, or rather the simplicial complex, is congruent to 1 modulo p to the a, where remember p to the a is the largest power p that divides the order of the group. It's the size of a p-Silo subgroup. So why is this called the homological Silo theorem? Well, it should remind you of Silo theorem 3 that says that the number of Silo subgroups is congruent to 1 mod p. Remember, the Euler characteristic is some sort of alternating count of the number of cells of each dimension. So, excuse me, the 0 cells correspond to p subgroups. So you can see this is somehow some analog of the Silo theorems. So far as I know, it doesn't imply the Silo theorems. I don't see how to, the Silo subgroups are certain specific vertices, so I don't see how it implies that. And there's a nice result. It has a number of proofs, not so important for this talk. I think when this thing really began to pick up was with the work of Quillen in '78. Quillen was Ken Brown's thesis supervisor. And he really started to study this complex as what he calls sort of a p-local, or other people maybe call it a p-local geometry for G. So I think Quillen's key observation that started this business is if G is a finite group of Lie type defined over characteristic P, so think something like the group of all invertible matrices over a p-element field, then this particular simplicial complex is homotopy equivalent to the building for G. And the building for G, of course, is very important for the understanding of the group G. In particular, the homology of this building is used to build the Steinberg representation, not me Steinberg, but the famous Steinberg, who is not related to me so far as I know, but I'll take credit for anything you're willing to give me credit for. So people since then have kind of viewed sort of the representations you get of the group on the homology of its p subgroup complex as some sort of analog of the Steinberg module. Of course, for the group of Lie type, this thing is homotopy equivalent to a wedge of circles, sorry, a wedge of spheres of top dimension. They're all the same dimension. And so there's only one non-trivial homology. In general, you have lots of non-trivial homology. And so what they look at is the virtual module you get by alternating the modules at each dimension. Another thing that Quillen showed is that this p subgroup complex is homotopy equivalent to the subgroup complex AP of G, where AP of G is the poset of non-trivial elementary abelian p subgroups, or p tori, Quillen called them. So these are just subgroups of the form ZP cross ZP cross ZP cross ZP. So these are particular kinds of p subgroups, and you can order them by inclusion, and they're closed obviously under conjugation. And the corresponding subcomplex is homotopy equivalent to the original one. And then Quillen, it was easier to identify this with the building, although it's still not the building on the nose. Later on, Buch introduced what he called the p radical group subgroup complex, which is another something in between these two guys. And that guy is the building on the nose and is also homotopy equivalent. And Quillen also formulated a conjecture, which is still open, and people are in finite group theory and combinatorics like very much. He conjectured that the p subgroup complex is contractible if and only if G contains a non-trivial normal p subgroup. Or equivalently, its p radical which is the intersection of all the p-Silo subgroups, is non-trivial. So one direction of this is easy. If you have a non-trivial normal p subgroup, multiplying by that subgroup gives you a retraction onto the subgroups which contain your normal p subgroup, and that retraction is order increasing, and so it gives you a homotopy equivalence between the whole complex and the subcomplex of those things which contain the normal subgroup, and that has a minimum, and so you can contract. So it's not difficult to show that if there's a non-trivial normal p subgroup, you can contract this complex. The other direction, of course, is not easy because it's open. So what is known about it? So Quillen proved this conjecture for solvable groups in his original paper. Aschbacher and Kleidman many years later proved the conjecture for almost simple groups, so in particular for finite simple groups. I believe this uses the classification. There are the strongest results to date, which are way too technical for me to either state or understand, are due to Aschbacher and Smith, where they reduced the conjecture to groups whose generalized fitting subgroup has only certain kinds of simple components. And that's all I can say because I don't know anything about this kind of stuff. Another thing that's kind of interesting is over the years, a huge number of homotopy equivalent subcomplexes have been introduced by people. So Quillen started this by looking at the complex of elementary abelian p subgroups, but people have had all sorts of other variants over the years. And in 1991, Ibanez and Webb proved that not only are these subcomplexes homotopy equivalent, but they're equivariantly homotopy equivalent. They're G homotopy equivalent to the p subgroup complex. So G homotopy equivalence is something stronger than ordinary homotopy equivalence. So I don't know, it's something I never saw in like a standard graduate level course. So let me just tell you what it means, though most of you may know what it means. So if you have two equivariant maps between G spaces, then they're G homotopic. What it means is you have a homotopy, which I'll write as HT. So HT is the function at time t, it's the slice at time t. It has to have the property that each of these slices HT, where t is on the unit interval, should be equivariant. So if you think of a homotopy as a map from x cross I to y, if you fix the t coordinate, then it should be equivariant. So that's a much stronger than just saying that they're homotopic. It says that the G action is preserved. In particular, if they're G homotopic, the homotopy factors through the quotient because of the fact that when you fix t, it's equivariant, you can induce a homotopy on the quotients. So I didn't say what is G homotopic, but you can guess what it means. You have, G equivariant maps in both directions that when you compose them are G homotopic to the identity map. It also implies that the homologies are homotopy equivalent as modules over the group. It's even stronger. It implies that the chain complexes are chain homotopy as G modules. So it's stronger than just that the homologies are isomorphic. You have a chain homotopy equivalence between the chain complexes. Another thing that's nice about G posets is if you compute the G invariants. So these are the G fixed points. So you take the chain complex with coefficients in some ring R. Because G acts on the simplicial complex, it acts on the homology on the chain complex, and you can take the G invariants, the chains which are fixed by G, or rather the cochains. I put a dot here. So this is the cochain complex. So what is a cochain? It's a map from a Q cochain is a map for, that sends each Q simplex to R, and it should be a co-boundary. Okay, and it's saying that it's G invariant means that if you sort of, permute their simplices by elements of G and apply the function, it doesn't change the answer. Well, that's the same thing as a function on the quotient complex to R. Okay, and so motivated by group cohomology is concerned with the functor of taking invariance. So motivated by group cohomology, Webb showed that if you take the orbit complex, its homology over the field FP is 0. So you can see that the homology of this guy is going to be connected to the homology of this complex of invariants. Of course, since we're working over FP, then this taking invariance is not exact, so group cohomology is going to be involved here. And Webb conjectured in 1987 that the orbit complex, so the p subgroup complex mod the action of G, conjectured that should be contractible. And the fact that it has acyclic cohomology in FP is sort of evidence. Okay, so this was first proved in 1998 by Simons. And he did it the following way. He showed that the fundamental group is trivial, and he showed that all the integral homology vanishes. And therefore, by the Hurewicz theorem and Whitehead's theorem, it's contractible. But of course, it doesn't really tell you how to do it. So Bucks gave an alternative proof using Best-Wiener-Brady style discrete Morse theory, and his proof is probably the closest to mine, but it's not so explicit. So it's not so easy for me to see exactly how similar they are. So, but basically, there are a couple of things that come up in his proof for those who know Best-Wiener-Brady style Morse theory, discrete Morse theory, which I won't try to explain. That theory is typically applied to polyhedral complexes, but here we just have a delta set, and we have these issues that the intersection of two faces is not necessarily a face. So he had to kind of play around with the definition of ascending link to take care of that. And the other thing which makes his proof less explicit than mine, even though I think that in spirit they probably have a bit in common, is that he does it inductively. He shows that the ascending links are orbit complexes for smaller subgroups and uses that's contractible by induction. And I'm going to basically just explicitly contract things. In fact, all these proofs do not use the subgroup p-subgroup complex. They use what's called the Robinson complex. This is a G-homotopy equivalent complex. Every proof I've seen uses this one, and I use it too. And so let me tell you what is that subcomplex. So the Robinson complex, which is introduced by Jeff Robinson, is the subcomplex of the p-subgroup complex, where you look at chains of p-subgroups which are all normal in the last one. So a chain of p-subgroups does not normally they don't have to be normal in the last one, but you can look at those chains which they are. This is a subcomplex, obviously. If they're normal in the last one and I start removing some guys, they're still going to all be normal in whatever the last one left remaining is. Each guy normalizes all the previous guys, but it's no longer the complex of a post set anymore. It's no longer that. And in their paper, Thevanes and Webb proved that this Robinson complex is G-homotopy equivalent to the p-subgroup complex, and therefore the orbit complex of the Robinson complex is homotopy equivalent to the orbit complex of the p-subgroup complex. So I'm really going to work at that one. Their proof uses Quillen's theorem A, or Quillen's fiber lemma, which is a sort of criterion that tells you if you have a map between posets with some certain property, then you get a homotopy equivalence. And they use a G-equivariant version of it. They proved the G-equivariant version of Quillen's fiber lemma in their paper, and that one of their main applications was to show that all previous proofs that things were homotopy equivalent to the p-subgroup complex are actually equivariant equivalences, because they all go through Quillen's fiber lemma. Okay, so what I want to do is I want to prove explicitly that this complex, the Robinson complex mod G, is collapsible via an explicit collapsing scheme in the sense of Ken Brown. Ken Brown collapsing schemes are also known as Robin Foreman discrete Morse theory. Robin Foreman was a professor of mine at Rice University when I was an undergrad. They came up with the ideas independently. Foreman formulated the thing in a different way. Then Chari came up with a reformulation of Foreman's theory in terms of matching, and Chari's theory is exactly the same as Brown's theory, up to slight modification of terminology, which I always forget the exact translation, but it's not that difficult once you put it back in your head. So let me just remind you of what is an elementary collapse. And to make things simpler, I'll explain what it is in a finite delta set. So what you do is you take a maximal simplex K, think of it as this sigma. Sorry, I have a finite, I said it wrong. My maximal simplex is sigma. So I have a delta set K, pretend this is a simplicial complex. I take a maximal simplex like the sigma, and I look for a free face tau. What is a free face? It's a face which does not belong to any other simplex. So for instance, this face here would not be free because it belongs to some other simplex, but this one is not. Now there's kind of an obvious deformation retract of a simplex to, well, in this, for instance, I can basically smush this face all the way to this vertex while leaving these guys fixed, as you kind of see in this picture. And you can do this in higher dimensions too. So given any simplex, you could choose one of its faces, and you can deformation retract everything to all the other faces. And if your face is a free face, you can then do this inside of your delta set by just fixing everybody outside of that face, and you'll get some sort of a deformation retraction. So being a free face, and so this is called an elementary collapse. And this is all part of Whitehead's theory of simple homotopy theory, which is interested in when you can get, when you can do your homotopy equivalence via elementary collapses. Okay, so a delta set's collapsible if it can be a finite delta set, if it can be contracted to a vertex by a sequence of elementary collapses. So you do one elementary collapse, you get a new delta set, then you do another elementary collapse, and you keep going until there's basically nothing left. Now, Brown introduced something called collapsing schemes to formalize his proof with Giogan that Thompson's group F is of type FP infinity. And he also gave a proof, and his complete formalization appears in this paper, where he proves that groups with a complete rewriting system are type FP infinity. I don't really want to get into what that means now, but I'm going to tell you what a collapsing scheme is in the special case of trying to collapse a finite delta set to a vertex, because that's the only case that I need here. And again, this is completely equivalent to Robin Foreman's discrete Morse theory. It's just a different language for it. And I guess I'll kind of use the Robin Foreman sort of formulation of things. So I'm going to fix my vertex V0 that I want to collapse everything to. And then what I'm going to do is I'm going to partition all the simplices of X other than that vertex into two types. I'm going to have certain simplices or cells which are collapsible. In order to be collapsible, it should have dimension at least 1 because there's no place to collapse a vertex to. And then I have other cells which are called redundant. And these cells are going to be the free faces that I collapse my collapsible cells along. And each collapsible cell is going to have a distinguished redundant face. Here it is in a picture. So sigma is my collapsible cell, and it has a distinguished face, which is going to be called its free face. And the distinguished face is really distinguished in terms of like which face it is on the simplex, like its opposite vertex I. Remember, in a delta set, it's possible that this face and this face get glued together. But in the way we talk about the redundant face really refers to both this face and its position on the simplex. And each redundant cell should be the face of a unique collapsible cell. So in other words, there's a bijection between redundant cells and collapsible cells. Every collapsible cell has its free face, which will be redundant, and every redundant cell is a free face of a unique collapsible cell. And then there's a condition that I need, which is the following. I build a digraph whose vertices are all the simplices other than my distinguished vertex V0, and I have two sorts of edges. I have up edges and down edges. An up edge goes from a redundant cell, which is a free face of, say, sigma to sigma. So sigma is collapsible, so it has a free face, and I draw an up arrow, which I'm making blue. And then for every face other than the free face, I do a down arrow, which is drawn as red. Okay? So you have up arrows from a redundant face to the guy that it's the free face of, and you have down arrows from a collapsible simplex to all its faces other than its free face. And my condition is that this graph should be acyclic. This is the key point. This graph must be acyclic. What acyclic just means there are no directed cycles. There could be undirected cycles, but no directed cycles. So I have an example of such a thing on the next page. So let me see. So here's an example. So I have this very ridiculously, obviously contractible simplicial complex here. It has a triangle and then one edge. And my distinguished vertex is going to be vertex 4. My collapsible cells are going to be these yellow ones, 1, 2, 3, 1, 2, 1, 3, and 1, 4. And my redundant cells are going to be 2, 3, 1, 2, and 3. The blue up arrows tell you who the free faces are. So 2 is the free face of 1, 2. 3 is the free face of 1, 3. And 2, 3 is the free face of 1, 2, 3. So hopefully that's clear. And now you can check that this graph is acyclic, right? There are no directed cycles. I think you can just stare at this and you can see that there are no directed cycles, right? Kind of you eventually end up over here at the end of the day, right? Everybody kind of ends up, any path that you can think of gets stuck in this sink, any directed path. Okay, now the way you're going to collapse this thing is you're going to totally order all the collapsible cells, sigma and tau, in such a way that if the dimension of sigma is less than the dimension of tau, then sigma should be smaller than tau. Or if they have the same dimension and there's a directed path from tau to sigma, then sigma should be less than tau. So for instance, this is an ordering of the sort I want. So first of all, 1, 2, 3 has to be the biggest because it has the largest dimension. 1, 2, 1, 4 has to be the smallest because there is a directed path from 1, 2 to 1, 4, and there's a directed path from 1, 3 to 1, 4. So according to this rule, 1, 4 must be the smallest. 1, 3 and 1, 2 are, you could choose any ordering you like on them because they don't have, they have the same dimension and there are no directed paths between them. And the fact that my graph is acyclic means that we can't totally order things in this way, right? So you have a partial order, which lexicographically orders first by dimension, and then by whether there's a path in this acyclic digraph that gives you a partial order that you can then topologically sort to a total order. So that's the idea, okay? And then what we're going to do is we perform our elementary collapses on collapsible cells, starting from the biggest one in this order and going down. And the way this order is defined, you're going to see always guarantees that when I get up to a collapsible cell, its free face is free in what remains. Because the way that these paths are defined guarantee that whenever a redundant cell is a face of some other cell, that other cell must be bigger than the guy for which it's the free face. So let's just do it on this example. And I think you'll get the idea of how this works. I think if you try to write the general proof, it doesn't make sense, but you could just look in this example. Okay, so the free face of 1, 2, 3 is 2, 3. Since there are no other three-dimensional faces, it's certainly not the face of anybody else. So I can elementary collapse along it. That means I smush this side into here, and all I'm left with is this. Okay, now I'm supposed to look at 1, 2 next. I can clearly elementary collapse 1, 2 using this as my free face. I could also collapse 3, 4 here as my free face. Notice if I want to collapse everything to 4, I could not have chosen what to do 1, 4 first. 1, 4 is supposed to have free face 1. If I tried to do 1, 4 along free face 1, I would have to, this guy was not free because it belongs to 1, 3 and 1, 2. So I'm not, you see that 1, 4, 1 is not a free face of 1, 4 and that's why this guy has to be smallest in the order. So if you think about it, what could go wrong? The thing that can go wrong is maybe my guy like 1, 4, he might be the face of some other collapsible cell. If he's the face of a collapsible cell, that cell either has higher dimension, but that means the cell is bigger. But sorry, I should say it's free face. I said it wrong, sorry. So let's say I want to collapse 1, 4. Its free face is 1. So the problem is it might be a face of some other guy, say of the same dimension. But if it is, that guy has an arrow to him, and that guy will be bigger. So therefore, I cannot actually collapse this guy along 1 until I've gotten rid of the guys which are before it in the order. So that's the idea. So if I follow this order, I can collapse 1, 2, 3. Then I could collapse 1, 2. Now the next thing I'm supposed to collapse is 1, 3. Now suddenly 1 is free because I got rid of 1, 3 and 1, 2, and I can collapse it. So the basic way this works is whenever you're trying to collapse a collapsible cell, its free face is not a face of any cell except those which are bigger in this order. And since I got rid of all the guys which are bigger than it in this order, it's safe. And that's exactly why we have the down arrows send guys to their faces. So that way it will be bigger than that way it will be bigger than anybody whose free face is a face of it. That's the idea. Okay, so it takes a little thought, but that's how it works. So now I'm going to tell you very explicitly how to collapse the Robinson subcomplex of the p-subgroup complex using one of these schemes. So again, the Robinson complex is the vertices are the non-trivial p-subgroups, and the simplices are chains of p-subgroups where everybody's normal in the biggest guy. Okay, and then I'm going to put brackets around a chain for the G orbit of this chain. Remember I'm interested in the quotient of this thing by the action of G, so I'm looking at orbits of these chains, and I put brackets around it for the order. This is going to be a delta complex. The ith boundary is you just omit the ith vertex, the ith subgroup. So it's just induced from the boundary in the simplicial complex. And notice this is actually a regular CW complex. What does this mean? If you restrict the gluing, it's 1-to-1 on the faces. This is just because each of these faces, you can look at the sizes of the subgroups that appear, and because these guys were increasing order, if I remove different subgroups, I get a different list of sizes. And so no two faces are actually identified. This is also important for bucks too. This is gluing along triangles together, and you never glue two faces of the same triangle, but you still can have that the intersection is not, another cell. Okay, another notation I need is NG of P0 through PQ. That's just going to be the intersection of the normalizers of these PIs. So what is it? It's just the stabilizer of this chain for the action of G. So NG of P0 through PQ is just the stabilizer of the chain P0 through PQ. In particular, because we're in the Robinson complex, PQ normalizes all these guys. So the biggest guy in the chain is always in the normalizer. Okay, so who do we choose as our distinguished vertex? Well, vertices are p subgroups. Well, they're orbits of p subgroups under conjugation. So vertices of this complex are just conjugacy classes of subgroups. And if you had to choose one particular conjugacy class of subgroups in a finite group of p subgroups, you really only have one obvious choice: the conjugacy class of p CELO subgroups, right? That has to be our distinguished vertex. Come on, CELO theorems are all we have about p subgroups. Of course, that's going to be who it is. And now I have to tell you which other orbits of chains of subgroups, which are all normal in the last guy, are collapsible and which are redundant. So this is the part that makes my proof different than previous proofs. I tell you exactly who's collapsible and who's redundant and what order to do them in. So that's the idea. So when is it going to be collapsible? It's going to be collapsible if PQ is P CELO in the normalizer. What does this mean? This means I cannot add another subgroup at the end and make this bigger and still be in the Robinson complex. So what it means is that there's no bigger subgroup which normalizes all these guys. And therefore, I cannot make this longer by adding somebody at the end. Maybe I can make it longer by adding somebody in the middle, but I cannot make it longer by adding somebody at the end. That's what this kind of says. And otherwise, I will say it's redundant. So if there is somebody I can shove on at the end, then it's redundant. So the collapsible and redundant hopefully is clear. Collapsible means that the biggest subgroup I have there is the largest thing I can put there and maintain the property that I'm in the Robinson subcomplex. And redundant means there actually is a way to make it bigger and stay in the in the Robinson complex. And then you can guess, what the bijection is. If it's redundant, there's somebody I can put here and make it bigger. So do that. And that's going to be sort of the way you match redundant guys to collapsible. But you have to show that this meets all the rules. And there are basically only two things used in this proof: the CELO theorems, basically that everybody's contained in a p subgroup, and all the contained in every p subgroup is contained in a CELO subgroup, and also that all the CELO subgroups are conjugate. Those are the two things I use. I don't use the numerical result. And the other thing I need about p groups is that every subgroup of a p group, finite p group, is subnormal. So that just means if you have a proper subgroup of a p subgroup, then its normalizer is strictly bigger. So that's the other property I need. That's not a difficult property of p groups either. It's not that okay. It's usually one of the things you see when you do the CELO theorems, and then you get into p groups. So these are the only two properties of p groups that I need, and I need both of them. Okay, so maybe before I go to the next page, anyone have any questions? I think I can see them in chat or something. Need me to slow down, remind them what collapsible means. Okay, so the idea is we're basically going to look at maximal cells. In a maximal cell, I obviously can't make it longer by adding somebody at the end, so it's going to be collapsible. I'm going to remove the last guy, and that's going to be my free face. And then I'm going to kind of keep proceeding in this way. And eventually I'll get down to the CELO subgroups. So I have to check all the properties. What are the properties again? Maybe I'm going to just go back for 1 second. The properties I need is each collapsible cell has a free face. Each redundant cell is a free face of a unique collapsible cell. And if I build this diagram where I can go up from redundant cells to the guy that they're the free face of, or I can go down from a collapsible cell to any of its non-free faces, I need an acyclic graph. These are the properties I need. And then I can collapse things by choosing some order with the property that big cells are first. And among cells of the same dimension, I get smaller if I'm following directed paths in this acyclic graph. Okay, so first of all, If I take a vertex as a p subgroup, and if I have I need all the vertices to be redundant except for the class of CELO subgroups. So if I have a proper p subgroup, then it's contained in a p subgroup, in a p CELO subgroup Q. So by this fact about all subgroups of a p group being subnormal, the normalizer of p and q is a larger p subgroup, which is contained in the normalizer in G of p. And that means it is redundant in the sense I had before. So all my vertices are redundant, but I really need to use this fact that the normalizers get bigger. If I have a collapsible cell, the free face is going to be, as I said, remove the last guy. If I remove the last guy, then because PQ plus 1 normalizes all these guys, because the Robinson complex are the guys where the biggest guy normalizes everything, this PQ plus 1 isn't the normalizer of all these guys, and therefore PQ is not a p-CELO subgroup of this normalizer because there's a bigger one. So this is really redundant. Remember, being redundant just means that there's nobody I can add at the end. Since PQ plus 1 was somebody I could add at the end and say Robinson, this guy is redundant. Now, if it is redundant, then I need that it's the free face of somebody. And here's where the CELO theorems come in. So if it's redundant, then what I can do is I can look at the normalizer in G of my guys P0 through PQ. So this is the guys which normalize all of these guys. And I can take a CELO subgroup. And because I assume that being redundant means PQ is not a CELO subgroup, this is a bigger subgroup. Being redundant means that really I can throw this guy on. And so now I throw this on. Now you may object and say, hey, wait a second. This might depend on which CELO subgroup you choose. But all the CELO subgroups of this normalizer are conjugate in the normalizer. But the normalizer stabilizes P0 through PQ. So I can conjugate this chain by somebody which takes PQ plus 1 to some other CELO subgroup and fix the earlier guys. And so I do not change the orbit in the orbit complex. And from that, it's easy to see that this is well defined. So the fact that any two CELO subgroups of the normalizer are conjugate means that it doesn't matter which guy I throw in at the end, I get the same orbit. And then, of course, it also doesn't depend on P0 through PQ. That's easy to check. The trickier bit is that it doesn't depend, once I fix P0 through PQ, on which CELO subgroup I take. And this is why I really need to be working with the orbit complex, because then when I use the normalizer, I fix this part and I move this guy to the other p-CELO subgroup. So that's the way I think of this. Maybe I think I moved by accident. Maybe I'll just try to draw a picture of what I'm talking about. So your objection might be, hey, I have PQ. It's contained in some p-CELO, but maybe I could have chosen some other p-CELO subgroup instead. But these are p-CELO subgroups of the normalizer, of the stabilizer of this chain. So therefore, I can find somebody which stabilizes this chain and conjugates this guy to here. And that means the orbit under conjugation of those two cells is the same. So in the orbit complex, I'm talking about the same guy, even if I'm not in the original complex. So that's the idea here. And that's what kind of saves the day. Maybe drawing that picture makes it clearer. And this guy really now is collapsible because this guy is a p-CELO subgroup of P0 through PQ, and therefore it's a p-CELO subgroup of this smaller subgroup. And you can also check that each each redundant face is a free face of exactly one collapsible cell, because basically all we can throw in at the end is a CELO subgroup of the normalizer. So this requires a little argument. Maybe it's not worth going to. So what I claim is if there's nobody I can throw in on the end, then PQ plus 1 is actually a CELO subgroup of the normalizer here. And so the construction I said before would pick out this guy. And the reason why is if it's not, then I can find something which normalizes the first Q guy, and it contains this guy. And then because of the fact that every subgroup of a p-CELO subgroup is subnormal, well, I'm going to end up saying that this is not a p-CELO subgroup. I decided to do it by contradiction here. What I said is take a CELO subgroup which contains it. This guy is going to be contained in the normalizer within Q of itself. And since Q is inside the normalizer of the first Q guys, and this is inside the normalizer of the last guy, this is in the normalizer of all of them. But being collapsible means that this guy's is a p-C-less subgroup of this normalizer, so it must equal this. But if it's self-normalizing in Q, it must be Q, because every proper subgroup is subnormal. So anyway, don't worry about this. It's a technical argument. But the point I'm saying is, if you take a collapsible guy, you remove its biggest subgroup, and then you do the construction I said before of putting a Q subgroup, C-less subgroup of the stabilizer of the first Q guy, P0 through PQ, you'll actually recover your original guy. So the only thing that's left is to check that this digraph is acyclic. So what is our digraph again? Again, what the digraph is, I'm going to just go back again. The digraph is, for each collapsible cell, you have an up edge from the free face and a down edge to every non-free face. And I need that graph to be acyclic. And what we're going to do is I'm going to define the height. And this idea of height also appears in Bux's paper. And it also appears in Simon's proof. All the proofs use somewhere, the size of the biggest subgroup in the chain. So we define the height to be the size of the last subgroup in the chain. And what we do is we look at the height, and this is obviously independent of which orbit I take of chains, because if I conjugate this guy, the very biggest guy is going to be conjugate to the very biggest guy, and that doesn't change the size. So this is a well-defined function on the orbit. And if we look at a collapsible guy, then what happens? Its free faces, I remove the last guy. Well, if I remove the last guy, it goes down, then this guy's PQ is a strictly smaller subgroup. Now, if I take any other face, I remove somebody who's not the last guy. And so this guy is the same last guy, so the height doesn't change. So what happens is the height goes up along blue edges. Whenever I go from a redundant face to its collapsible guy, I add a strictly bigger guy at the end, so the height goes up. But when I go down, the height remains the same. So what's going to go around in a cycle is, well, what I claim is in a cycle, you have to go up at some point. And once you go up, then your height goes up. But if your height goes up, and then when you start going down again, your height doesn't change. And so when you go in a circle, your height is going to be bigger than your original height. And that can't happen. So to explain why, notice that the height never decreases along it. First of all, the height never decreases, because as I said, a down edge preserves the height, and an up edge increases the height. Secondly, down edges decrease the dimension. So if you just use down edges, you're eventually going to reach a vertex. You can't go down, or a minimal. Anyway, the dimension goes down, so at some point, you're stuck. And if you're stuck, you can't get into a cycle either. So the only way you can have a cycle is you have to use at least one up edge. But if you use any up edge, the height goes up. And then it never goes back down again, because no edge brings you down. So if sigma lies on a cycle, its height is strictly less than its height, which can't happen because the height is a number. And so that's a contradiction. So it's acyclic, and therefore you can collapse this. So what I think is nice about this proof compared to the previous ones is it's really very explicit on the contraction. My feeling is that if you look at Bux's proof and you do the induction, it's probably doing something very similar. I mean, he doesn't explicitly tell you which guys to match up, but it wouldn't surprise me if you chase all the details that it's similar. So I think his proof is certainly the closest in spirit to mine. Nonetheless, even in Simon's proof, I somehow feel that his proof of simply connected also uses some of these ideas. But I think this is really very explicit and the sort of as clean as you can make it in that sense. And there's no induction. You know, I would have liked to draw an example of this, but the problem is, for this to be interesting, your p-CELO subgroup, you know, you shouldn't have a normal p-CELO subgroup, and your p-CELO subgroup shouldn't all be cyclic, because otherwise this complex would just be a vertex. And so once you want that your p-CELO subgroups have size at least p squared, and they shouldn't be normal, then you know you're already getting something that's getting pretty big. So that's why I didn't draw an example. But that's pretty much it. So thank you.
All right, thank you very much. Okay, thank you, Ben. Are there any questions for Ben? So you mentioned something about between a Brady Morse theory or something like it. So where could you say a little more about it? You know, so
that was the approach that Bucks used. Where did I say it?
But I saw that their version of it. I mean, it was only written for cubical complexes. Is this not right? You know, so and you're working with.
Well, I don't, maybe in the original paper, but I don't know. I think at some point people have done it for polyhedral complexes. It's, I mean, you know, you just need this height function. It should be affine on each of the cells, and you use some conditions on ascending
Okay,
links.
I didn't know that. I mean,
or at least that's what Buck says, and I didn't go and try to find the earliest sources of this, but I don't think being a cube, he sort of says it works for polyhedral stuff. And
yeah,
I don't, and he kind of sketches why. I don't see any reason why it wouldn't. The issue here is that it's not polyhedral because you get these multiple edges. You get that the intersection of these triangles do not have to be triangles.
Right, but I mean, this is a matter of subdivision. I mean, that doesn't bother me as much.
You can subdivide it, but that's a little bit different. You can subdivide it. It's true. You can subdivide it to make it simplicial. But then you run into different issues. I think you would have trouble defining the height that way because you change sort of the combinatorial structure. And I think it's much messier. In particular, you're no longer able, it's not so clear how you could use the CELA subgroup. So that's not what Bucks does. He really defines an analog. He has what he calls embedded ascending links. He has two kinds of ascending links, and he defines this link in a different way. And he works with that. I think if you try to subdivide it, it would kind of make it messy to define the height, because then your simplicial complex would look like chains of chains, chains of sets of chains. It just looks like a bit of a mess. It's true you can subdivide it, but I think it makes the combinatorics much worse, and that's not what he does. And instead, he shows the ascending links are like these for smaller groups.
Sorry, Matt, are you there, Matt? I thought that you tried to say something while Ben was speaking.
No, the Besvina Brady was written for cellular, or not cellular, polyhedral.
Is that right?
Yeah.
Okay.
It was also written rather densely. So.
Okay, I think probably my memory.
But I think the issue here is links are messed up. Like, if you have like the multiple edge issue, or
so it's not
the links get messed up. So you have to do something about it.
I understand what Ben means, because this takes you slightly out of the category even of what people usually mean by polyhedral complexes. But in fact, what it showed, it had the flavor a little more in the spirit of, what is it called, Foreman's Morse theory, because I mean, even though you're using something like an honest height function, right? But there are some versions of Morse theory which use like more general combinatorial devices.
Well, that's what I'm using as well, but you can reformulate it. Foreman's Morse theory is the same as this Brown collapsing scheme. So, I mean, the way you build the height function from these Morse things is exactly what I just said. You get this acyclic matching, you turn that into a post set, and then you lexicographically order by height, followed by the post set ordering. I think Matt Zaremski has a paper where he explains how you do this.
I mean, that actually sounds a little artificial, yeah, I mean,
it is a bit artificial, and it's not necessary to do.
Right.
But at the end of the day, I mean, Brown does it, also organizes it slightly different, but it's equivalent. And so, yeah, so I like to talk, so you don't really need to talk about the height so much. If you really want to, if you just want to formulate how to use it, you never need to mention the height. If you want to formulate the proof of what's the order to collapse these things, it's convenient, I think, to put the height back in. But there's certainly a dictionary between these. I mean, Foreman did use some sort of, height function, and then the combinatorial method in terms of these matchings erases it. And then the matching criterion is almost exactly the same as Brown's up to a minor translation.
Okay.
But the nice thing about Brown is Brown did it in his paper for simplicial sets rather than for polyhedral stuff or regular cell complexes, which is, I think Foreman does regular cell complexes, but Brown does simplicial sets. And if you have a post set and you have a group acting on it, the quotient is a simplicial set. It's a delta set, but it's a simplicial set where the degeneracies are all trivial. And so Brown's setup was really the most convenient for me.
Okay, very good. Are there any other questions or comments? Okay, if not, let us thank Ben again. Thank you. So I'll stop the recording now so that